Hi, I'm Caleb, member of the Teen Advisory Board with the Howard County Library System, and today I'm going to teach you counting lists of numbers. So when you hear the word counting, you might be thinking, hey, I learned how to do that when I was 3 years old. But this is for competition math, which means counting problems will be a lot more complex than just going 1, 2, 3. So counting the number of elements in a list of numbers is an important skill as basis for competition math combinatorics. So let's start with a very simple list of numbers, which is the integers from 1 to 3049, and we're counting 1, 2, 3, 4, 5, 6, 7, 8 all the way to 3049, and this is obviously just 3049. Now, that's an extremely simple example, but we can use this as a basis to other more complicated lists. So for example, here we have the integers from 34 all the way to 175. So you wouldn't want to count individually and be like 1, 2, 3, 4, 5, 6, and then all the way to 175. That would be highly inefficient. So we want to make it into a form such as this, where we start with 1 and we count by 1, so that we can more easily count it. So let's say 1, 2, 3, 4, and just look at it from there. Alright, so we have 34 and 1, 35 and 2, 36 and 3, 37 and 4. You might see a pattern, and that pattern is that the difference between the number that we're counting and the number of numbers that we've counted so far is 33. So 34 minus 1 is 33, 35 minus 2 is 33, 36 minus 3 is 33, and so on. And the reason the difference is constant is because here we're adding 1, and here we're also adding 1. So if you add the same number to two different numbers, the difference between them is going to stay constant. So since we know that the difference is going to be 33, we can just subtract 33 from all of the elements. And note that subtracting from all of the elements won't change the number of elements, so we know that that's okay. And we can just do minus 33, and we get 1. Minus 33, we get 2. Minus 33, 3, and so on. And then we can just do the last element. And 175 minus 33 is 142. So now we know that the list 34, 35, 36, 37 all the way to 175 has the same number of elements as the list 1, 2, 3, 4, 5 all the way to 142. And we know that this list has 142 elements, so this list also has 142 elements. So this is a way to count a list of numbers that doesn't start with 1. So we can also generalize this by looking at subtraction. So if we do 175 minus 34, which you could have thought of earlier on, we actually get 141, which is not equal to 142, obviously. So why does this occur? Well, subtraction calculates the number of steps between two numbers. So by doing this, we calculated the number of steps between these two numbers. So there's going to be 141 steps, right? But the number of elements is one more than the steps. So for an easier example, say we have 5 lampposts. To calculate the distance between the two end lampposts, we look at the steps, or just subtract, and then we get 4. But in order to find the number of elements, or the number of lampposts, we add 1. So same goes for any number n. if we have n steps between the elements, there are a total of n plus 1 elements. So for counting lists of integers that increase by 1 each time, we can express it as a plus 1, a plus 2, and a is just the number that the list starts with, and we go all the way to b minus 2, b minus 1, and b, where b is the number that it ends with. So in this list case, it will be 175. So we know that if we subtract the last number from the first number, we get b minus a, and that's the number of steps. But from this example, we learned that the number of elements is always one more than the number of steps between the elements, so we add 1. And this is a very convenient formula to calculate the number of elements in a list like this. So we can try it out. If we just plug the numbers in, so we get 175 for b, 34 for a, and then have to remember to add 1, and then if we calculate it, we still get 142. Alright, now let's do a more complicated example, which is where the gaps are not 1. So here we have a constant difference of 6. Every time we go up by 6. So how do we represent this in this form, where we can count it easily by just looking at the last element? So for this, we can use the fact that the difference is 6. So 16 we can just represent as 16. 22 is 16 plus 6. 28 is 16 plus 6 plus 6, which means 16 plus 6 times 2. 34 is 16 plus 6 times 3, and you see the pattern. So these we can just put as 16 plus 6 times 0, and then 16 plus 6 is just 16 plus 6 times 1. And here we can clearly see a pattern, and it's the number that's being multiplied to 6 that's increasing by 1. So we know that we can use that, and we have to represent 370 as in this form. So this is going to be 16 plus 6 times some number n, and then if we solve for n, we just subtract 16 from both sides, and then we get 354 equals 6 times n, divide both sides by 6, and then we get n equals 59. So we know that 370 we can represent as 16 plus 6 times 59. So we have a list of numbers in the form 16 plus 6 times n, where n ranges from 0 to 59 inclusive. So this list of numbers, we can ignore the 16s because that doesn't really contribute to anything, and we can also ignore the 6s. That will still maintain the number of elements. So now we have a list of 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way to 59. All the way to 59. And this list is much easier to figure out how many elements there are. So we know that if we just look at this part, this list starts with 1. So we know that this list contains 59 elements, and if we just add the 0 in, we get 60 elements. Now, there's a different way to utilize the differences, the constant differences in numbers. That will, of course, still give us the same answer, but it's a bit faster. So we can come up with a formula that is general to any arithmetic sequences. So here we had it increased by 6, increased by 6, increased by 6. It keeps increasing by 6 until we get to 370. So we can use that fact to calculate how many gaps there are, and then we know that if we add 1 to it, we are going to get the total number of elements. So let's calculate the gap between 370 and 16, which is just subtraction. So 354, but that doesn't mean there are actually 354 gaps, because each gap is 6. So we divide by 6 to find that there are 59 total gaps, and then if we add 1 to it, that's 60. So we can generalize this. Let a, b, and n be integers. Then we can represent an arithmetic sequence, which is just, arithmetic sequence just means each element has a constant difference between the consecutive elements. So in this case, we're going to represent the constant difference as n, and then all the way up to some number b. So what we did here was we calculated the difference, b minus a, and then we divided it by the constant difference between the consecutive elements. So that's going to give us the number of gaps, and then if we add 1 to it, we get the total number of elements. So that's another formula that, if you understand how it works, is going to be very useful. Alright, let's do one last example. So this is counting the number of perfect fourth powers between 10,000 and 100,000. So again, we want to represent it in some form of a list that we can easily see how many elements there are. So from this we can't really decipher anything, so we need some numbers. Let's just find the smallest perfect fourth that would fit in this range. So perfect fourths are in the form n to the fourth power, where n is an integer, and if we do 10 to the fourth, we'll get 10,000, and by between, it usually means inclusive, so including these bounds. So we know that 10 to the fourth is going to be the smallest number that's in the range, and by some experimentation, or guess and check, we can find that 17 to the fourth power is 83521, and 18 to the fourth power is 104976. So this we can see is greater than 100,000, so it's not going to be one of the ones that we're considering. So we know that since 83,521 is less than 100,000 and greater than 10,000, we know that this is going to be the greatest number in our list. So this is the smallest, this is the greatest. Now we have a more manageable list. 10 to the fourth, 11 to the fourth, 12 to the fourth, all the way up to 16 to the fourth, 17 to the fourth. And now we know how to count this list. We don't care about the fours, and we can just use b minus a plus 1, because it's increasing by 1, and it's just all integers. So we find the gap, and then we add 1 because we want to find the number of elements, and then we get 8. So there are 8 perfect fourth powers between 10,000 and 100,000. Alright, that's it for counting list of numbers. Thanks for watching, and I hope this video helped.